Okay, so let me go ahead and start. Today we're going to go ahead and introduce something called a phasor. And this is not the Star Trek variety of phasors, the pew-pew kind. This is the rotating vector kind of phasor, and it's going to be useful for looking at how these components like inductors, capacitors, and even resistors behave in the presence of AC or alternating current. So to start with, we're going to begin with a circle. Actually, I'm going to start with a coordinate system, and then we will add a circle to that. Oh, this circle has seen better days. Okay, so we're going to go ahead and start off with this circle, and we're going to start off here at what we would say 0 degrees. And as we rotate around this circle, we hit up here at 90 degrees, where we change our angle by 90 degrees. We keep on going, we hit 180 degrees. And we keep going again. We hit 270 degrees, and come full circle, we hit 360 degrees. Okay, however, degrees is not as useful as radians would be for calculating this. So instead, we're going to use radians for this. And over here at 0, we would be at 0 radians. Up here, we would be at pi over 2 radians. And over here, we would just be, once we complete 180 degrees, we would be at pi radians, and keep on going. We hit 3 over 2 radians, 3 over 2 pi radians, until we come back around and complete our full circle at 2 pi radians. Okay, and the reason we care about this is because if we go ahead and look at our AC waveform, and we look at a sine wave, specifically one full cycle, we can start here at 0. We reach the peak at pi over 2. We cross the 0 axis at pi. We reach the lowest point at 3 pi over 2. And we complete this revolution around this circle. I got some feedback. At 2 pi. And if we take our circle and we go ahead and draw a vector, and if we let this vector rotate, we have just started to create our sine wave, right? If we allow this vector to rotate around our circle in our coordinate system here, then we've just gone from 0 degrees to 90 degrees. And we let that continue rotating, and we go back down to pi, or here 0 at the crossing, at this point. And then we keep on rotating this vector and we hit the bottom over here. And then as we come back up and reach 2 pi, we're back at where we started at 2 pi. Okay, so this is, we can represent this sine wave as this rotating vector around our circle, and we can specify at which point we've rotated around by the radians. Okay, so I can go ahead and also put a couple of points here and say at 0, our vector is facing that way. At this peak over here, our vector is facing upward. When we come back around, our vector is now facing to the left. When our sine wave hits the lowest point, our vector is facing downward. And once we've completed one full cycle, we're back at where we started, facing to the right. So you can see that we're allowing this vector to rotate until we're back at where we started. And so we've just started representing our sine wave. Now, this rotating vector is what we call a phasor. Now, another important point about this is that it is the projection of this vector along the along the y-axis that gives us our instantaneous value. Is the instantaneous value of our sine wave. So if you look over here, when our phasor is at 0 degrees or 0 radians, the projection on the x-axis is 0. Just looking at this axis here and looking at the projection on that axis. Now, when our phasor now rotates to its peak value up here, denoted by this red phasor, notice that now the instantaneous value is at its max point over here. That's the projection along the y-axis. Okay, when we allow that phasor to again rotate over to 180 degrees and we go back to 0, again, the projection on the y-axis tells us the instantaneous value, which is at 0. And again, when we get to our lowest point over here, the y projection of our phasor at this point is the maximum negative value that we get, or down here. and then back until we get to where we started, and we know that the projection on the y-axis is going to be 0 over there. Okay? Now, for our phasor in general, we can go ahead and specify our frequency as the radian frequency using omega. And for the instantaneous value, as being the projection along the y-axis, gives us an equation where we can go ahead and use our trigonometric functions to define that. And I'll use voltage for example. Where we can say the instantaneous voltage, or the voltage at some time t, is equal to our peak voltage times sine of omega t. Now, the nice thing about doing this is that we can keep frequency out of it until we want to include it in here. Now, we're used to defining frequency as hertz. As cycles per second. And we've been looking at that in LT Spice and using that thus far. 1 hertz would be 1 cycle per second, 2 hertz would be 2 cycles per second, 1 kilohertz would be 1,000 cycles per second. But we'll use omega as the radian frequency, which is dimensionless. And omega will just be 2 pi, the amount to do 1 complete rotation times our frequency. And frequency, as far as the period is concerned, is 1 over the period. So we can also say that omega is equal to 2 pi over the period. So let's go ahead and let's put this in terms of a voltage that I think we're all really familiar with. What comes out of our outlet? Now what comes out of our outlet is 170 volts peak. And we already talked about this. We have three different ways we could specify this. 340 volts peak to peak, 170 volts peak, or 120 volts RMS. And we can pick whichever one we want to use depending on which is more beneficial for us given our circumstances of what we're solving for. And the frequency of this AC voltage is 60 hertz, or 60 cycles per second. So if 1 second has elapsed, I expect to see 60 cycles has occurred within that 1 second. So if we want to go ahead and express this voltage, and let me go ahead and calculate that out. 0.0167 approximately seconds. Then we can go ahead and put that into our formula to find the instantaneous value of this voltage at any point. So V of t is going to be equal to our peak voltage, which is 170 volts, times sine of 2 pi times our frequency times t. And so now we can go ahead and have a nice simple formula that gives us the instantaneous voltage at any point along our sine for any given moment in time that we would want. And so this is typically how you would go ahead and define your instantaneous value, using this equation. Okay? So it's not a hard thing, but I know when I first saw this, it was a little hard to wrap my mind around it because like, whoa, you got a moving, rotating vector. Yes, you do. However, generally speaking, when we're going to be looking at these things, we just care about the relationship between two of these vectors. And we'll see that in a minute. Before I continue on, are there any questions about this? Okay, so why do we care? Well, let's go ahead and let's talk about inductors in AC. And I think if we're going to talk about inductors in AC, it's good to have a starting reference point. That reference point is going to be something a little simpler, which is a resistor in AC. So let's go ahead, let's give ourselves an AC voltage source. I'll just call it V.
Professor, I don't know if you saw, but you got a couple questions in the chat about the last thing.
Well, they took too long, so too bad. No, I'm just kidding. Let me get back to that. What do we got? Can you show the previous paper real quick? Yeah, of course. Was it this one or this one? This one. I think this is the one that really drives the idea home for me, at least, because you're dealing with something that is tangible. It's, well, to a certain degree, it's more tangible if you stick your finger in the electrical outlet and get a zap, and then you really understand what's going on. But yeah, for sure, for sure. And do we know the values between the points? Oh, between which points? Are you talking about, let me pull up the previous. Are we talking about, oh, I don't want to bleed through the paper. Are you talking about, let's say, points here? And here, and here, and here. Are you talking about all of those points? Yeah, so this allows you to solve for that. Let me do this. Okay, so if I put these side by side, if we say that this sine wave is 170 volts peak AC, then this equation that we wrote out to describe the voltage coming out of our electrical outlets gives you all of these points, provided you enter in what time you want to know what that is, right? So this is why I was saying the projection along the y-axis is your instantaneous value. If let me actually draw a couple of different examples here that I think are going to help. Right? So this one, obviously the projection on the y-axis is 0. However, this one is a little larger. Well, that's this point in our sine wave. If we allow that vector to rotate a little more, if the phasor rotates a little more, then now the projection along the y-axis is greater still, and we're roughly around this point until that phasor reaches our max value, which would be 170 volts peak. I guess I could say this, 170 volts at the max point. And our sine function gives us the value along the y-axis that we care about. So that's why we're taking sine times the peak voltage, the max value when this phasor is all the way up, times sine. And I bet another good thing that I can show bet if I type in phasor animation, right? So what they're doing is they're plotting along the this graph where you have time versus, say, voltage, or time versus our instantaneous value. I hesitate to say voltage because you can use this for current, you can use this for anything. But our instantaneous value is a little more generic of a way to say it. So you can see over here the pink line is the instantaneous value. It's the projection of the vector along the y-axis. And so when you look at the sine wave that's being produced here, you're really just looking at the instantaneous value going up and down. It's a little bit like, and this might be worse, if I take a bicycle wheel and I spin that bicycle wheel, and then I take the bicycle wheel and I turn it so it's facing you directly on, you just see a point along that bicycle wheel just going up and down, right? Do I have anything round that spins? No, I don't. Nothing around here. Yes, thank you for asking that. Okay. Now, before we talk about an inductor in AC, really good idea to look at a resistor in AC because it's quite a bit simpler. And so I'll go ahead and use time versus voltage so we can see this relationship, and then we'll go ahead and draw it in phasor form. Now I'll do voltage in blue. And so we know with this AC voltage applied to the resistor, if we wanted to go ahead and plot V sub R, and I don't really have to care about frequency at this point. Over here we have our voltage applied to the resistor. And I'll go ahead and just call this V max. V max or V peak, the maximum voltage that you go ahead and apply to this resistor. And so we would like to say, well, what is the current doing? Well, as the voltage is increased, as it's applied to the resistor, the current is also going to go up. They're proportional, and they're proportional according to Ohm's law. So let's go ahead and let's say V max is equal to I max, I max, times the value for our resistance. Right? This is the relationship between the current and the voltage. We just take the current, multiply it by the resistance, and we get the voltage. Now, if I go ahead and plot what the current looks like in relationship to the applied voltage, I'll use red for my current. Depending on the value of the resistance, that's going to determine our magnitude of the current, right? According to Ohm's law. So I'll call that I sub R. And this current also reaches some max value. I'll call it I max, as I did down here. Now, if you notice in this drawing, both the current and the voltage are at 0 at the same point. Same thing when the current goes up and the voltage comes up and then they go back down. They cross the 0 at the same time. And again, they go down to the lowest value and then they come back up to 0 again. Well, the same thing is true for the peaks. Both the voltage and the current reach their max value at the same exact point. And they reach their minimum value at the same point. Now this makes sense to me because the relationship over here, Vmax is equal to Imax times R. Now, because these both reach their max at the same point, they both cross the 0 at the same point, and they're proportional all along everywhere in between, we say that these are in phase. There's that phase word again. Okay, we say that they're in phase because they reach their max at the same point, they reach their minimum at the same point, they cross the 0 at the same point. For all practical purposes, they are the same. They just have a different proportional scaling relative to each other. Okay, and that is governed by this equation. Now, an easier way to represent this, and an easier way to discuss this, and an easier way to see the interaction between the phase of these two sine waves is with a phasor. And so to do that, we can go ahead and just draw our phasor diagram. And we can go ahead and draw, I'll use a blue one for the voltage, and I'll keep it consistent. Our voltage was higher, I guess, than our current. They are two different values. One is in voltage and the other one's in amps. And so I'll let the blue phasor be representative of the voltage. And then I'll draw another phasor to represent the current. So it's kind of a very clever way in order to represent the relationship of the phase of these two sine waves. Okay, so that's ultimately why it is powerful to use a phasor diagram to represent these two quantities, because you can see things that are otherwise a little more difficult to see than if I just drew a bunch of sine waves on a graph and said, "Oh yeah, tell me some things about the phase relationship between these two sine waves." And I started with the resistor because the resistor is the easiest to see. These are both in phase. And it doesn't matter where I draw that moment in time. Over here, this point I used at our zero crossing. So this is the phasor diagram for here and here and here. But if I wanted to look at it at its max instantaneous value, I could draw these up here and here. And for all practical purposes, this is the same thing. It's just a different moment in time that I went ahead and I drew it. And that radian frequency can be used as well here. Okay, so now boring is what I would say, because these are both in unison with each other. Both at any point in time, both of these vectors, these phasors, are in phase with each other, and they're going to rotate around the center of that coordinate system for our phasor diagram in unison. But what about an inductor? Now I'm going to go ahead and start with the end result of what the relationship is between current and voltage when you're looking at an inductor. So I'll give ourselves an AC voltage source applied to our coil of wire, or our inductor. Our inductor is going to be denoted with L, and our AC voltage I'll just call V for now. Well, if we go ahead and plot this, let's start with the voltage. Actually, let me do another half cycle. And so this is going to be V sub L, the applied voltage. Well, as it turns out, the voltage actually reaches its max value before the current does. And the difference between that is 90 degrees. So we would say this is 90 degrees out of phase. Now, there is a reason for why this is happening. Now, if you remember, an inductor opposes a change in current. Okay, so it's actually going to be useful for us to look at the minimum rate of change and the max rate of change for our applied voltage. In fact, I'll use, do I have a few other colors around here? Blue, and I'll stick to green and black. And let's say we look at V sub L. And we go ahead and I'll use black for the min rate of change. And I'll use green for a max rate of change. Well, where's the min rate of change as far as this applied voltage to our inductor? Well, the min rate of change would be when the slope is the least. That occurs up here, and that also occurs down here and up here. Slope of the tangent line is the smallest at those points. Where's the max rate of change going on? Well, that's occurring over here, and I'm using green for that. And that's occurring here when we cross the x-axis going in a negative direction. And again, our max rate of change occurs here when we're going positive, and again down here. And now, what's our back EMF doing during all of this? If you remember from an inductor, when we have a change in current, and we will have a change in current whenever we have a change in voltage, we get an opposite voltage that's induced that counters the original change that produced it, right? That we call the back EMF or the counter EMF or the CEMF. It's the induced voltage, and it's always opposite of the change that caused it in the first place. Well, the back EMF is doing this. And if you notice, it looks like the back EMF is going to cancel out the voltage applied in the first place. And that's why we end up getting our our current staying high at this point in time. Because when we have the max rate of change for our applied voltage, we get the max rate of change for our back EMF. Our back EMF is going to try its hardest to maintain that current at its highest point. So let's go ahead and say that when V sub L tries to go low, the back EMF keeps the current high. And similarly in the opposite direction, keeps I low. Now, this is the explanation that the book tries to give for this. But the end result is that the voltage and the current are 90 degrees out of phase with each other. And in fact, it looks like the voltage reaches its max before the current reaches its max. Now, there's a little memory device that's been around for at least 70 years called Eli the Iceman. And in this little mnemonic device actually tells us quite a bit about inductors L and capacitors C. Now E is for electromotive force, which is a voltage. And I, of course, is for current. And so what this little tool tells us is that voltage leads current for an inductor? Or we could also say current lags voltage for inductance. These are both saying the same exact thing. If I go back and simplify our voltage and current relationship for an inductor, then you can see that the voltage reached its max value before current, or in other words, the voltage leads the current. Or you can say that the current falls behind the voltage. And don't get confused, because time is increasing in this direction. So if I reaches its max over here, then it's actually behind the voltage. Don't just look at it from the perspective that, well, voltage is behind current. It's not. The voltage is leading the current. The voltage occurs at a time point sooner than the current does. I'll say that again. The voltage occurs at a time earlier than the current does. So we say that the voltage leads the current. Or you can say that the current happens after the fact or lags the voltage. Okay, so both of these are saying the same thing. Now what I didn't include here is by how much. By 90 degrees, because it's by a quarter of a cycle. 1/4, 2/4, 3/4, 4/4 is one cycle. Well, the difference between here and here is a quarter of a cycle. And a quarter of 360 degrees is 90 degrees. So this mnemonic device ends up being actually quite useful because it lets us remember that the voltage comes before the current for an inductor, and also for a capacitor, it's the opposite. The current actually happens before the voltage, or the current leads the voltage. Now, using a phasor diagram makes this a little more clear to visualize, understand, and actually use. Because if we go ahead and plot our phasor diagram, notice if we just pick any point in time, let's go with here where I is at 0. Well, if I'm at this point in time for current, then our phasor should be projected along the y-axis at 0. And at that same point in time, when I is at 0, V is at its max value. And the max value as projected on the y-axis is up here. And how far are they separated from each other as far as phase? Well, it's a quarter of a cycle, or 90 degrees. Well, that's exactly the angle that is made here. I'll be a little facetious and say 90 degrees right there. Now, the cool thing about doing this is it doesn't matter at what point in time, the relationship stays the same. So whether I draw it like this, or I draw it like this, I'm getting the same story, which is that these two phasors are 90 degrees apart from each other. And so you can allow these two to rotate and it tells us the entire story of that phase relationship between the voltage and the current. And I can probably find a pretty good animation of this online. Or maybe I can't very easily. It should be... Now, this one has a resistor in there, but But don't worry about the resistor. Just look at the blue and the green arrow. They stay at 90 degrees apart from each other as that phasor rotates around. And then you can see that their projection along the y-axis is the result in that diagram of voltage with respect to time. Okay? Okay, and I'm going to go ahead and I'm going to cut that there. We're going to finish this up next class. We still need to talk about reactance in relationship to the inductor, but hopefully the phasor notation kind of makes sense. It's going to allow us to see those relationships of voltage and current for an inductor, and similarly current with relationship to voltage for a capacitor. Okay, so hopefully that makes sense, and we will see more of that next class. We'll take a 10-minute break now, and then when we get back to lab, we'll go ahead and we'll finish up that diode lab that is due next Tuesday. Okay? All right, I'm going to go ahead and stop recording.